This lesson's on domain and range. Now first of all, here we have a relation, and the domain of this relation is the possible values that the horizontal axis could have. In other words, the possible x coordinates of all of the points in that relation, whereas the range is a set of values that the y coordinates could be. Because the x and the y coordinates can have only certain values, we need to learn how to write this, and we'll learn that in the next slide. Let's start with an example here. We have a number line graph. As you can see, the variable is x. We have closed points on this number line graph, which means that x can be between a and b, including a and b. Notice how we would write it like that. Next one, we have what's called a set notation. Now we can write this using a set of numbers, a set of values, that is. We need to use squiggly brackets. First of all, you write down the variable. You specify, look, the variable is x. That line is read such that, and then we put the conditions. The conditions were the x is greater than or equal to a, but less than or equal to b. And it's read as the set of all x such that x is in between a and b inclusive. Another way to describe the values that x can have is using interval notation. Now again, x could be between a and b, and it could be a and it could be b. So in this case, because we're using closed points, we are going to be using square brackets. Notice how it's written. We write down that x belongs to, and now you write down the interval. It starts at a, it ends in b. It can be a, and it can be b, and that's why we use square brackets. Let's look at another example here. In this case, x would have to be less than a, notice the open point, or x would have to be greater than or equal to b. Notice the or, by the way. Again, set notation, x such that, we put the conditions, x less than a. But how do we write the or in maths? Or use the u symbol, u standing for union. So we'll put the u, and then followed by the next condition, x greater than or equal to b. Now if you had to write it in words, you would write it as the set of all x such that x is less than a, or greater than or equal to b. This time, let's write it using interval notation. Now, whenever you have an open point, you must use a round bracket. Whenever you have plus or minus infinity, you must also use a round bracket. So in this case, we'll write it as x belongs to. Now x, if you think of it from left to right, starting at minus infinity, goes up to a, and then, or it could also be from b up to positive infinity. Notice that it cannot be a, so we put a round bracket around a. It can be b, so we put a square bracket next to b. But we never ever use square brackets for positive or negative infinity. Now in this slide, you'll be given 4 different number line graphs. What I would like you to do is press pause every time a number line graph appears, write down the set notation and also the interval notation, and check your answers afterwards. Press pause now. The next graph could represent how much it costs to park a car at a car park. So if you have a look at the horizontal axis, we have time in hours, and the vertical axis, we have charge in dollars. So if you were to park your car between, say, 0 and up to and including 1 hour, it would cost you $5. Now, between 1 hour, and up to 2 hours, it costs you, looks like that will be $9, and so on. So the question is, what is a domain? What is a range? Well, first of all, the domain, in this case, we're using the variable t. So it will be t such that, and have a look, what are all the values that t could be? Can it be 0? No, there's an open point there, but it can go all the way up to 24, and it can be 24. Next one, range. This time the range, the variable is c. So we must write down c such that. This time we have a discrete set of numbers for c. So we have 5, we have 9, we have 11, 13, 18, 22, and 28. Here we have a function. If we have a close look, there's a close point at -1, -3. So first question is the domain. What is the smallest value that x can have? The smallest value that x can be is -1, and it can be anything greater than or equal to -1. So domain x such that x is greater than or equal to -1. Or in the interval notation, notice a square bracket around the -1 next to the -1 and the round bracket after infinity. Now if we consider the y-coordinates could be anything from -3 onwards. So have a look at the range, the way it's written, and the interval notation. Notice the square bracket next to the -3 and the round bracket after infinity. So that's saying that y could be anything from -3 all the way to infinity. Let's consider the next function, which looks like a quadratic. Now there are no restrictions on what x could be. So in this case, x could be all the way from -infinity up to positive infinity. Now when you have no restrictions, when you're writing down the domain, you would write down the x such that x belongs to the set of real numbers. Now that means that x could be any real number, no restrictions. When you have to write it, if you were to write it down in interval notation, you would write down the x belongs to, and you write down the set of real numbers, so r. Notice the way that r was written, with 2 lines there. Let's now consider the y-coordinates, the range. The y-coordinates could be all the way from -infinity, have a look, it's getting up to a maximum of 1, and now to start decreasing again, all the way back to -infinity. So you write down y such that y has to be less than or equal to 1. Or in interval notation, y belongs to, and have a look at the notation, all the way from -infinity up to and including 1. Next example, please only have a look at the graph on the left. Go from left to right. What are the possible values that x could be? It looks like x could be anything except 2. So when we write down the domain, you say x such that x is not equal to 2. And if you would like to write it in the other form, simply just x not equal to 2. Done. The same with y. Y could be anything except 1. So that's how you write down the range. Let's have a look at the next function now. As we go from left to right, the x values can be all the way from -infinity up to and including 8. So the domain, you write down x such that x is less than or equal to 8. In terms of interval notation, you would put from -infinity all the way up to and including 8. Notice the round and square bracket. Now range, look at the screen there. The y-coordinate is decreasing, now it's increasing, and now it's decreasing again, reaching up to the value of -2. So it means that y could be anything greater than or equal to -2. Whereas in terms of interval notation, you would say that y can be anything from -2 up to infinity. Notice the square bracket around the -2. To fully describe a function, we need both a rule and a domain. If you have a look there on the screen, you have f of x equals x squared. Now we don't have the whole parabola there. We have a starting point. So the equation is your rule, but now we have to specify what part of that function do we have there. And you state the domain next to it. The x values can be anything from -2 onwards. So x greater than or equal to -2. When you're writing down conditions, you only ever write down the domain next to it. You never ever write down the range. If a domain isn't specified, we use the natural domain. What's a natural domain? It's the largest part of the set of real numbers for which your function is defined. So in this section, what I recommend is please get your calculator, go to graph, and graph your functions as you see them on the screen. In terms of setting a viewing window, I would recommend go Shift F3 for viewing window and press standard, which goes from -10 to 10. We are going to be going through a number of functions that you should become familiar with. The first one is f of x equal to x squared. Notice that my graph has the arrows missing at the end of the function, but you assume that it continues. So in this case, there are no restrictions on x, which means that x belongs to the set of real numbers. Now the next function is f of x equals a square root of x. I would like you to go and plot this one in your calculator. Do press pause, this is important. So please press pause now and go and plot it. Did you get what's on my screen? Is that the way that your function looks? And if you were to plot that, is that what you would plot? Obviously, you would put the arrow at the end. Well, what's on the screen there is missing some information there. So my question is, what happens when x is 0? Square root of 0, that is 0. So how would you indicate that point there when x is 0? What would you do? Well, you would put a close point there at 0, 0, indicating that that point is included. Now, in terms of the domain, that means that x could be anything from 0 onwards, so x greater than or equal to 0. The next important function for you to know is 1 over x. Now, x is in the denominator. The denominator is x. The denominator cannot be 0, which means that x cannot be 0. If you have a look at the function there, if you were to draw the line x equal to 0, which is a vertical line, in this case it would be a vertical asymptote. The last function here is 1 over square root x. Now we said before that when you have square root x, x has to be greater than or equal to 0. But here in this case, square root x is in the denominator, which means that x cannot be 0. X cannot be negative. So in this case, x would have to be greater than 0. And if you have a look at the graph there, you will notice that the function is defined for positive x values. There is no graph there when x is less than or equal to 0. Let's go through another example now. In this case, we have to state the domain and range of each of the following functions. We start with f of x is equal to square root of x minus 1. Now it would be useful to have this table handy. Square root x minus 1 looks pretty similar to square root of x. The inside of the square root has to be greater than or equal to 0. So what we have to do is we have to write down that x minus 1 has to be greater than or equal to 0. Then you solve like you normally would in an inequality. So therefore the domain is x such that x is greater than or equal to 1. Now in terms of finding the range, I'll recommend that you plot it in your calculator. Now notice that I put a close point there. When x is 1, the function becomes 0. And as you can see from the graph, the y values, the y coordinates, are all positive or 0. So you say that y has to be greater than or equal to 0. We have another pretty similar example here. I only added a plus 2 at the end there. So in terms of finding the domain, we have to consider the square root of x minus 1. Just like before, x has to be greater than or equal to 1. In terms of the range now, so if we were to plot the graph, you will notice that y has to be greater than or equal to 2, because when x is 1, that whole thing becomes 2. So how can we justify this? Well, the square root of x minus 1, that's greater than or equal to 0. You add 2 to it, the whole thing is greater than or equal to 2. So the range, as we said, y such that y is greater than or equal to 2. Here we have another example. Now remember, since we're dealing with real numbers only, whatever's inside a square root has to be greater than or equal to 0. In other words, it cannot be negative. So, x squared minus 9 greater than or equal to 0, you might go down this path, and if you do, you end up with x greater than or equal to plus or minus 3. Uh-oh, what does that mean? Nothing. That's incorrect. We have to start it again. Now, x squared minus 9 is a quadratic. We're going to call it g of x. What is the shape of this quadratic? Concave or convex? Well, convex. Now we must draw a sign diagram to see when that is positive. To be able to draw a sign diagram, we have to find when it's 0. So you solve that equation, we end up with x being plus or minus 3. So the sign of g of x. We write down the zeros, which are plus and minus 3. So it's a quadratic. And I'm going to draw here a little diagram on the right hand side there. So just to give us an idea, which means the sign is plus, minus, plus. Now the question is, when is x squared minus 9 greater than or equal to 0? Well, we look at the sign diagram, and that means values that are less than minus 3 or equal to minus 3 or greater than or equal to 3. So therefore the domain for our original function, which is f of x, would be x such that x less than or equal to minus 3 or x greater than or equal to 3. Now I'm going to write the function again just to have it on the screen. Now there we have the graph. As you can see, it is not defined for values between minus 3 and 3. If you were to pick any of the values there between minus 3 and 3, put it into the square root of x squared minus 9, you'll end up with the square root of a negative number. Now what happens when x is plus or minus 3? Well, if we substitute it, you notice that we get 0. That means on the graph I'm going to put a close point there. And the same for when x is 3. Again, we get 0, noticing that I'm putting another close point on the graph there. So, what is a range? If we have a close look, we notice that y, in this case, is greater than or equal to 0. And this concludes this question. In this example, the denominator cannot be 0. In other words, 2x minus 6 not equal to 0. So we solve for x, we end up with x not equal to 3. So our domain is x such that x is not equal to 3. Now we plot the graph, have a look. There's a dotted line there. That dotted line, if you remember, is called a vertical asymptote. Now in this case, you'll see the cursor on the screen, and as x approaches 3 from the right, consider what's happening to the y-coordinate. The y-coordinate is increasing. The y-coordinate goes towards positive infinity. Consider what's happening now as x approaches 3, this time from the left. The y-coordinate is approaching minus infinity. This time, consider what's happening to the y-coordinate as x goes towards positive infinity. The y-coordinate is getting smaller and smaller, and it's approaching 0. Consider what's happening as x approaches minus infinity. The y-coordinate is also approaching 0. The y value was never 0. So as you can see, I'm drawing a dotted line there. That is called a horizontal asymptote. So the range was, or is, y such that y can be any value except 0. Last example. In this case, we have a square root appearing in the denominator, which means that 4 minus 2x has to be greater than 0. So we proceed to solve for the inequality, in this case, solve for x. And as you can see, in this step, we're dividing by negative. Notice how the direction of the inequality changed, which means that x has to be less than 2. In other words, domain is x such that x is less than 2. Notice the graph here, x equal to 2 is a vertical asymptote. Notice that the function does not exist for values of x that are greater than 2. Now our range, what values could y have in this case? Well, if you look at the screen there, y started from positive infinity, and it's decreasing as we go towards the left, and it's approaching y equal to 0, so it means that y has to be greater than 0 in this case.